Welcome to another video on STM32 Super Basics. In this one I'm going to give you a very simple example on how to create a PWM signal. Something like the one you see on the screen here, if I remember what I did to create this one when I recreate it now. We're going to be using the STM32 Cube IDE and the hardware abstraction layer, the normal way of using things in here. So inside STM32 Cube IDE, we start a new project. Okay, the part I'm going to use is the part I've got to hand, and it's one of the simplest parts which I like using for these demos because they don't have particularly complicated peripherals and therefore they're fairly easy to understand when we look at the basics. And it's the STM32 F030K6T6, which in normal times would sell for $0.627, but in these times you're lucky if you can even buy the things. Okay, so let's give it a project name, PWM, more traditional spelling, PWM demo. And that will put us straight into the device configuration tool. And then here you can scroll zoom in, scroll zoom out, whatever you want. And you will see in the clock configuration tab that by default HClock, the basic clock that drives stuff, is set to 8 MHz. Now we can change that if we want to, but I'm not going to. I just want you to remember 8 MHz is the basic clock. Okay, so how do we actually create a PWM signal? Well, PWMs are based on the timers, so if we look in the timers section here, there's numerous ones we could choose from, and I think they've all got PWM outputs, but I'm going to choose TIM3 because that's what I did before, not for really any special reason beyond that. Okay. And then you can see that each timer has multiple channels that can do multiple different things. And if I look, for example, in channel 1, then there's a PWM generation ch1, the channel 1 corresponding to this channel 1. So I'm going to select that. And you can see that it's picked PA6 as the pin that will output the PWM signal that we're about to create. So that side of things is already done. Great. Now, the way that the PWM works is that the main clock, which I just said is 8 MHz, is optionally divided down by a prescaler in the timer if you wish, and I am going to do that because if I divide it by 8, then the clock ticks that we are considering in timer 3 are a nice round 1 microsecond, so we're going to do that. And then when we generate the actual PWM signal, there are two magic numbers that we care about. There's the period, which is in numbers of 1 microsecond ticks, and then there's how long the high part of that period is, which is called pulse times the tick count. Okay, and you'll see that those parameters are represented here. So we have a period and we have a pulse value. Alright, now remember I said I'm going to prescale down. So in order to prescale down, you actually have to do 7, which you can represent it as 8 minus 1, which is a bit more obvious what you mean. The value of 0 prescales by 1, which is basically leaves the signal alone, so it's all offset by 1. So if you want to divide down by 8, then you really divide down by 7, but you can write it like that so that there's a sort of visual reminder that you really meant 8. Now this period here is when should I stop counting up in 1 microsecond tick intervals. So what's the overall span going to be of 1 PWM pulse? And in this case I'm going to make it 1 millisecond because why not? And that's 1,000 ticks. But once again, we need the magic -1 in this particular case. Okay. And then the only other number that we care about is the pulse number, which is how long is it going to be high for. Now I'm not going to make it a completely symmetrical waveform, otherwise it wouldn't be obvious that we've got some sort of PWM magic going on here. So I'll make it something like 250, which would be a quarter of the way through that 1000. There's no point in making this value more than 1000 because the counter will never get there. Once it gets to 1000, it will just reset in the normal way that a timer will do. So the sensible values here are from 0 to 1000, and I do mean 1000 for the pulse value. That will give you full DC output. 0 gives you full DC output. 1000 in this case gives you full DC output, which is to say one more than this number. But I'm going to start off with 250. And that, in fact, is all you need to generate the code that we want to generate. So I tend to do that just by closing this window, which will save it and then generate the code. It asks you if you want to save it. Yes, I do. Thank you very much. Do you want to generate the code? Yes, I do. Thank you very much. I'm getting all these pop-ups because I started a new kind of blank workspace for this demo. Usually you just put those away and ignore them and never touch them again. Right. Let's try and make this a font that you can actually read. Okay, so you can see in here the code has been generated that sets up the timer. And if you look in main, that setup function is called. Now that doesn't actually start the timer, it just sets it up. Now remember, when you're in these code generation tools created code, you can only add your own code between a begin and end zone. And there are many of them. Here's another one, begin, end, begin, end. If you write code outside the bounds of those begin and end bits, then if you rerun the device configuration tool and regenerate the code, your code that you added will disappear. So don't do it. Now there's a gotcha for PWM creation. Although it's based off timer 3, you don't start timer 3. Not quite anyway. The normal way to start a timer would be HAL tim base. I hit control space then to get the options, if you're wondering. Start. And then in this case I've only got one timer, so it's offering me up the option. That would be the normal way to start it, but it's not how you start PWM. If you want PWM to work, it's different to that. It is in fact tim PWM start. You'll be shocked to see. And in this case we have the extra parameter, which is the channel. So yes to tim3, and then here it doesn't know what you want, so we say tim channel 1, because we set up channel 1 of the timer 3 to be the PWM output. Another gotcha, don't just type in the number 1, because that macro expands to 0. So either put in 0 or use the macros that they've provided. Okay, let's get rid of that. Indent so that it looks like a professional wrote the code. And then we'll compile that and see what we get. We'll make an attempt at actually putting this into the device I've got running. Let's see how that goes. No, I don't wish to update the firmware on my ST-Link. Oh, excitement. Let's see what we've got. Yay! So you can see that there's approximately a 1 to 4, or well actually a 1 to 3 ratio between the high and the low. There's a 1 to 4 ratio between the high and the overall period, which reflects that 250 to 1000 in the numbers that we put in there. So that appears to be working. Let's make it so that it's high more of the time than it's low. So we'll change that 250 to maybe 800 or something like that. So we'll go back into the IOC file. Which is always very quick. Go back into timers, go back into timer 3, scroll down until we find the 250, and we'll change that to 800. Remember to hit enter. And then I can do save, or I can put this away, it doesn't really matter, or I can just build. It will save it, generate the code. That's getting irksome. and blow it into the chip at the same time. Let's see what we get when that runs. There it is, it's now high more than it is low. Fantastic. So we don't have to go into the IOC file, the setup file, and fiddle with it there. If we want to, we can change those numbers somewhere in here. So let's give a demo of that instead. TIM3, the where do I change somewhere between in the pulse is called CCR1 in this case. It's 1 because there we are, and I'll make it, oh I know, 500. We'll make it an exact split. Alright then, let's compile that. Only this time we'll say yes to a few defaults. There you go, you can see it's now 50-50 and I didn't have to fiddle around with the IOC. So even though in the TIM3 setup code it is indeed setting it up to be 800, that's getting overwritten subsequently by me manually setting CCR1. Now it may be that you want to do some interrupt things that are based on the edges of the PWM signal that you have created, and that's possible. In order to do that, I'll show you how to do that. Go back into here, make sure you're in timers, TIM3. Let's try and make this a bit more visible so you can see what the hell I'm talking about. So we're in the device configuration tool, make sure you go to TIM3, fiddle with your windows till you can see what you want to be talking about, and then you can see that we've only been dealing with the parameter settings here, but there are other stuff as well, including the NVIC settings. Can't remember what it stands for, but it's where the interrupts are enabled or disabled. So we'll say enabled. That is not enough to get the job done. What we also need to do is instead of calling HAL-TIM PWM start, we call the underscore IT version of that instead. So as long as the interrupts are enabled in the NVIC setup of the IOC file, and as long as we call HAL-TIM PWM start IT for interrupts, then that will generate interrupts. In order to find the name of the callback functions that are called from the interrupt service routine, the best way to do it, because there is one by default, even though this will compile even though we haven't written a service routine. So first of all it will generate the code, and it compiles without errors or warnings. Great. So it must know where to be going somewhere, and I'll show you how we find out. If we go into the drivers directory and then the HAL, not the CMSIS directory, and then the source because we want the C files, you can see for the various peripherals and subsystems like DMA and external interrupts and GPIOs and so on, there's also a HAL-TIM.c, and that refers to the timer and the PWM. So here is that, and you will find somewhere in here this one. There are two callbacks. One for when the entire pulse is finished, called pulse finished callback, and one for when it's halfway through, so in other words when we've got to the CCR1 point rather than to the ARR point. I'm only going to grab this one here, but you can take both of them, and you can see that it's declared here as __week, and that's kind of a bit like C++ overriding, where you can write the same function name if you wish and it won't say, hang on a minute, I've got two definitions of the same function. It just throws away the weak one and uses the one that's declared elsewhere. So I'm going to copy this minus the weak bit because I don't really want that, and then I'm going to paste it somewhere into main.c, and that will become the callback that happens at the end of every single pulse. So in other words, in this case, every millisecond. We need to find somewhere to put it, and it needs to be between a begin and end. I can either put it at the end, in which case I've got to declare it as a function prototype at the top, or I'll just put it somewhere near the top. So here's main, above there makes sense, and here's a begin end zone, so somewhere in here makes sense. So if I shove it in here, boink, there we go. Let's just check it compiles, we haven't done anything stupid. And then we're going to do something actually in here as well. Okay, so what should we do? I don't know. Let's actually change the CCR value at the end of every pulse. So we'll increase it, which changes the on time and reduces the off time. TIM3 CCR 1 plus plus, but that will overflow when it gets to 1000. 1000 is the maximum sensible value, which is actually ARR plus 1. So let's check that we haven't gone beyond ARR plus 1, because if we have, then it's just in the realm of invalidness, and loop it back down to, say, 0. So we'll check there. If TIM3 CCR1 is greater than the maximum value that it makes sense. It doesn't matter if it is, it just won't make much sense. ARR. Remember, ARR corresponds to pulse, and period, and CCR corresponds to pulse plus 1. So if the CCR value is greater than the period value, then we'll reset it. In other words, what we're saying is, if we're trying to make this bit here bigger than the overall pulse, don't do that because it doesn't make sense. TIM3 CCR1 equals 0. Good. Okay. So it doesn't matter much that we're setting it to 500 there. That's just going to be the starting value. Then we're kicking off the interrupts version of the PWM, and then at the end of every pulse, in other words, at the end of every millisecond, because we set it up to be a millisecond, this code will execute that will change the mark space ratio. Let's see if that does anything worthwhile. So we're building the code. Let's bring up the scope. It's gone to sleep whilst it's being programmed. Okay, it's changing kind of quickly, so you can't quite see what I can see on my scope, which is rather smoother, but it is doing it. Now I suppose if I slowed down the pulses so that it wasn't happening quite so quickly, that will make a bit more sense, but there you go, it is indeed doing it. So that's kind of a primer on the basics for getting up a PWM signal, and indeed going beyond that a wee bit and doing some things with interrupts at the end of each PWM cycle. I hope that was useful, and if not, sorry I wasted your time. And here we go, time to delve into video editing land, my favourite, and make this a thing that can be uploaded. Catch you soon. Bye.